Yes, I can start. Uh, Good evening. This is our third live problem solving session for the course Nanomaterials and Their Properties. I'm NPTEL from the MSc Materials Science Department at NPTEL. Uh, yeah. Next session is on 18th. So I think you already know. And I've already covered in the last two sessions. So the problem, the YouTube link will be uploaded on the YouTube channel and slides will be uploaded in the Google Drive. You can access from there. Okay, so I'll briefly recap the lecture. So in the last two lectures, we mostly covered the surface energy particles, how that changes on the crystallographic orientation or and the size. So for example, in the formula derived in class, U is your surface energy, which is total surface energy is your gamma times A. Uh, and if you're for a surface, if you're breaking n number of bonds, so total energy becomes n times gamma times A. Gamma is the rotation energy, A is surface area. Interfacial energy is surface area. So for a if you break a surface, you get suppose you get n number of bonds broken. So you can say those number n you can write as number of particles of your material. And this n you can write as using if the mass is n. So if you assume some spherical particle with some atoms sitting on the surface, so yeah, to get the value of n, I think here we are assuming all the atoms are sitting on the surface. The mass complete this. Let's assume all the atoms are sitting on the surface. So in this case, the mass would be number of atoms into volume of each atom and density. To get n, you can just divide the n by volume, atomic volume and density. So you get total surface energy per mole would be n gamma, yeah, so n over rho into gamma divided into A by V. A, now A is the surface area of this particle and V is a volume. So for a spherical particle, this value of A over V is calculated in lecture. Value of this A over V for spherical particle times A is equals to 4 pi r square. And then V is square by 3 pi r cubed. So A over B becomes 4 pi r square divided by 4 by 3 pi r cubed. Is r left there, is 8 over 4, is 3 over r. Radius 2 times r is diameter, so multiply both sides by 2, we get 6 over 2r is equal to 6 over d, where d is the diameter of a spherical particle. Okay, so for a spherical particle, you get a over u is equal to 6 over d. Okay. I wanted to this exercise, you can do this for any other particle shape and size. Mm, let's see examples. If you have a hexagonal particle, so my nanoparticle is a hexagonal rod shape. It will calculate the surface energy of those. So each face, if you see, I'm ignoring the end surface areas. So if you just calculate the surface area of the S surfaces. So it's a rectangle. Rectangle. A is the side length, and this is suppose L. So total surface area would be, so there will be six such faces. 1, 2, 3, 4, 5, and 6. 6 times A times L would be a surface area. So step A will some of the numbers. And so 6AL. Okay. Calculate the volume. So it's a hexagonal particle. So you have you can divide it into 6 little triangles. Right? And for each little triangle, you have A, A. You know, area of a little triangle is root 3 A square B square by 4. And since you have 6 such faces, uh, area of the space becomes 6 times root 3 A square by 4, which is 2. So 3 root 3 A square by 2. And you just multiply it with the length. Yes. Suppose this is an vertical. So this is your length L. A. So you just calculate this surface and the area of this flat face, which is this. So multiply this with the length, and you get the volume. Length L times E A square by 2. So your surface area to volume ratio becomes 6 L divided by 3 3 A square L divided by 2. So answers and we can say 2, 4, root 3. Okay. So your total surface energy, U surface was M gamma rho A over V. And so substitute the value of A over V. So this becomes M gamma rho into 4 by root 3. So this should be surface energy of 740. Next, he covered how surface energy changes depending on the face of the crystal. So if you have FCC crystal, which is centered cubic system, um, so yes, atoms are sitting in this, what is this? On the faces of each of these faces, center of each of this. So depending on which surface you put the crystal, say nanoparticle would be a single crystal, and depending on which surface it's on which of these crystal graphic orientation crystal plane lies on the surface, will have different surface energies. So example he showed was for uh, suppose you have the surface is broken along your 111, so gamma 1, oh, sorry, 100, 100 would be your display, you see, right? So here, it, what would happen? You count the number of bonds broken. So the number of bonds would be 1, 2, 3, 4, and the fifth. I divided by the area of this face, so A square. Similarly, actually, for this unit cell, each atom is only represented by 1/4 here. There should be only two atoms. Yes. So it's 1/4, 1/4, 1/4. You have one atom, and one is sitting on the surface. So I think there should be only two. So, and if you cut across okay. Mm, this. Okay. So for 111 plane, uh, this is a one plane which passes through all these different atoms, goes down. This is a 111 plane. How much atom does this one cut? So one, uh, 1, 2, 3, 4, and 2 takes center one. So 1, 2, 3, 4, 5, 6. According to the professor, it was 1, 6 over And you have the volume of this plane, sorry, the surface area of this plane. This is A, and this is A root 2. A times A root 2. So this is the surface energy. Again, I think this should be counted as one. Sorry, half. So one fourth. So you should get 2 over A root 2. And finally, we have one plane. So one plane is a bit more tricky to see. So it cuts the x-axis at 1, y at 1, and z at 1. So this, if your origin is here, this is the plane. You see, okay, this is the plane. So what all atom it cuts goes through this one, goes to the space. In the space, there's another atom sitting on center of the space. Should be here. So now again, if you just count the number of atoms, 1, 2, 3, 4, 5, 6, 6 divided by, and this is a equilateral triangle, and equilateral triangle with length root 2a. We just saw the area of a equilateral triangle, which was there, a square upon root 3 a square upon 4. So root 3 root 2a square upon 4. So you get root 3 a square upon 2. Root 3 a square. Again, I think he just multiplied the two dimensions. So he said this is root 2a, and we just multiplied root 2a, and root 2a, and we got this value. Okay, this is for a square, for a triangle. This is not a triangle. I think the trend would still be same. We get is 2 root 3, 4 root 3 by 2 square. And if you strictly count how many atoms are fitting, you get one third here, 60 degree. One third here, 60 degrees. So 1/6 here, 1/6 there, 1/6 there. So half atom there, and you have one half half here, half here, half here, plus 3 by 2. Then you get 2 atoms. It should be 2 3 by square. Mm. Biggest value. Where we will to the I think this is the best. Yeah. So much. We also, this is the densest packed plane of FCC. So you'd expect high energy here. Um, uh, for nanomaterial, so these phases may not be exactly along the crystallographic direction, and if they're at any random angle theta, the surface energy becomes this 2 times u cos theta plus sin mod theta, and if you plot this, you get that value. Surface energy u. Yeah. Reduce the question is reduce the volume to surface. I think this will be covered in the two lectures. I'll go. We can reduce this first. Surface to volume ratio for a cone. Mm, Putting surface to volume ratio for cone. Cone. This is a conical particle. Imagine circular base. Can also have rectangular, triangular, or other types of faces. L. This is H is the height. This will be this R. H is the vertical height from the vertex to the center of the circle. And if you know the surface area is this the area of this bottom face. This is pi r square. And your curved surface area, which is pi times r times L, your slant length, L, pi r square plus pi r L. And using Pythagoras formula, yeah, h square plus r square is equal to t square. So L becomes under root h square plus r square. Okay. We can simplify it a bit if you assume h and r are equal. So L becomes 2r square to root 2r. Yeah, the diameter becomes equal to the height. What the diameter of the radius becomes equal to the height. You get this relation. And this becomes pi r square plus pi r L square plus pi square. Volume is one third the volume of the cylinder formed by this cone. So one third pi r square into h. This is the volume. Uh, just a tip: whenever you have cone or a pyramid, its volume is always one third the size of a cube form, cubed or a fixed form. So if you had a pyramid with a rectangular face, again you assume a cube, rectangular cube, and you calculate the entire volume, and one third volume segment with uh, pyramid. So where again the volume of a cone is one third the volume of the cylinder circumscribing it. Or you can say, okay, so surface upon volume ratio becomes root 2 pi r square plus pi r square divided by pi r square. H is again, if you're assuming H same as R. I think I got disconnected for a second. Let me share the screen again. I don't know why my Zoom screen just Zoom disconnected and got reconnected. Okay, I'll go over few of the steps again. So the surface area of a cone we calculated is the surface area of the base times the surface area of the curved surface area. Surface area of the base is pi r square. The curved surface area is pi r. Using Pythagoras, you can get relation between L less than R. If you assume radius is equal same as the height, you get relation between L L and R directly. Substitute the value of L here in this formula. You get this as your total surface area. Volume of a cone is one third the volume of cylinder in campus encapsulating it. Encapsulating it. Yes, yeah. So this is your volume, surface area by volume ratio becomes so root 2 pi gets cancelled, r square cancelled, we get root 2 plus 1 divided by r, and there was a 3 here. Two. So it's 3 here on top. So 3 root 2 plus 3 over r. It should be surface to volume ratio for a cone. Uh, Next, in the second lecture, we talked about how surface curvature affects the surface energy. So he showed how the Gibbs free energy delta G changes for a soap bubble. So the same formula applies here. So delta G is the pressure difference between outside and inside times the volume. And the pressure difference for a soap bubble is 2 gamma by R. Okay. And we have one more definition, which is curvature, represented by kappa. is just 1 over r. So kappa is the radius of curvature. Okay. And for convex surfaces, this is a surface particle. For convex, you take surface, the radius as positive, and for concave, this would be a particle. So for concave, you have negative value of surface energy. Next, he calculated the vacancy concentration depending on the curvature. So I won't know the derivation. This is the formula you get. Your vacancy concentration total is your vacancy concentration per bulk times 1 minus your atomic volume omega times radius of the particle r. No, this is gamma divided by r kBt. Okay. So if your r tends to infinite, so you get a plane surface, you get your bulk uh, xv becomes your bulk, x total becomes your bulk density concentration. However, if your surface is convex, so for convex surface like this, your radius is positive radius, so the total vacancy concentration becomes bulk 1 minus omega gamma by r kBt. So obviously this is less. We're subtracting something from the bulk concentration, so this value is less than bulk concentration. And for a concave, where you have negative curvature, the R is negative. The total vacancy concentration becomes C bulk plus 1 plus omega kBt. So this is greater than the bulk concentration. So your concentration, vacancy concentration for total vacancy concentration for on cave is greater than vacancy concentration for bulk, which is greater than the vacancy concentration for convex. Mhm. The concave is the greatest. So what happens due to this is, suppose this is your surface of your particle. Uh, this is your concave surface, so negative. This is your convex positive. So your vacancy concentration is highest here. lot of free vacancies compared to here where only few vacancies exist. What will happen due to diffusion? You can assume a vacancy is diffusing here or your atoms diffusing to these vacant sites. So your mass will diffuse toward the concave, concave location. And slowly, due to this diffusion, this radius will decrease and this will become something like this. Eventually, the entire particle, you just see in this area, it will become flat. But if you see the entire particle, it will become spherical, transition towards one spherical particle. If you allow diffusion to take place. The last thing he covered was how the lattice parameter changes depending on the size, um, size of the particle. Mm, so the equations of delta A by A is 4 times gamma K 3D. So as your particle size decreases, D decreases, so your change in delta A, delta is a change, so change in lattice parameter also increases. So for a bulk, suppose this is the bulk lattice parameter. So as you go down to lower particle diameter, this will be a delta A. And as you go down, the diameter is decreasing, the delta A is increasing. As you move along this direction, the diameter is decreasing, and the delta is increasing. Mm, Why surface atoms have higher entropy? In, uh, so entropy you can also imagine as freedom to move. So all the atoms sitting on the surface, they are loosely bonded atoms. Okay. So they are pulled in this direction, this direction, this direction, but nothing on the top. So they are loosely bonded atoms. So they have higher freedom to move. So higher freedom results in higher entropy. Since there are fewer bonds, they have more freedom to move. And which parameter of nanomaterial plays key role in enhancing their properties, like heat capacity, diffusion, catalytic activity, and electrical resistance? This is your surface to volume ratio. Are you sure? Since again, if you have a lot of atoms sitting on the surface, they are loosely bonded, so it's more catalytic activity. These atoms uh, want to form bond with other atoms. So suppose we have carbon monoxide, it would want to bond with the surface atom, thus promoting catalytic activity. If your surface area is higher, we just saw they have higher entropy, so they promote diffusion. Electrical resistance again, since the surface area is larger, you have more barrier for the electrons to move. Uh, so increasing your resistance. I'm not sure how heat capacity directly works. Mm, I think they would have more freedom to vibrate, so heat capacity would definitely change. Yes, the surface area to vibration. So we have some practice questions. Surface energy arises due to uh, the main reason is due to number the broken bonds on the surface. That's the reason, and the total surface energy depends on the crystallographic orientation. But the reason for the surface energy, why the surface energy comes up, is due to unsaturated or broken bonds. Mm, which factors determine shape of nanomaterial? So here again, the shape of the nanomaterial depends on which how the lattice how it has different lattice structure. So different lattice systems would have different surface energy around different planes, and it will try to minimize the surface energy. So it will take the shape which minimizes the surface energy. So most important factor the surface energy. Diffusion has nothing to do with shape. Lattice parameters. Lattice parameters is depending on the radius, not the distribution. Yeah, just the surface energy. Nanoparticles exhibit high tendency to centering even at room temperature due to. So we just saw nanoparticles have very high surface area. So uh, very high surface area, and they have very large surface vacancy concentration. It's V is inversely proportional to diameter of the particle, right? So if you decrease the diameter, your surface vacancy concentration increases a lot. So the curvature of the nanoparticle or indirectly radius is the reason why they have very high tendency to center. So I think we also showed this in the lecture. This is charity images. So you have two nanoparticles which come in contact with each other. Since there is large vacancy concentration on the surface, just where the particles would meet, and you have negative curvature. So particles would make their atoms would migrate from concave to convex, sorry, convex to concave surface. The concave, this is a convex. So atoms would migrate here, forming this neck, and finally they would fuse together, big, bigger particle. Okay. So number of broken bonds per unit surface area depends on, again, we just saw this depends on the crystal orientation for different, we just saw for FCC. So depending on so FCC, so FCC depending on different where along which direction the particle breaks, surface is exposed. We have different number of bonds broken per unit surface area. For FCC, the surface energy of atomic different different atomic planes are involved. What are they? So So I found a good derivation for this question here. According to that, what you get is gamma 110, gamma 100, and um, so explanation is which is the most densely packed space that has the lowest energy. So 111 has the with the densest packed plane. Next is 100, and this is your least densely packed plane. So least densely packed, the most. So for STC, gamma 111 would have the least energy. So okay. I'll have time in the next session. I will go over the derivation a bit more. Just try to find the definition. Okay, I'll go over this in the next session. Surface to volume ratio for a cylinder with radius R and H is. So we have a cylinder, and your surface, the curved surface area is 2 pi R, 2 pi R L, 2 pi R L. So L किसी का H, 2 pi H, and your volume is pi R square into H. Volume is equals to pi R square H. Think they have ignored the surface area of the face. what you get is surface area 2 pi S over V plus 2 pi H divided by I R square H, which is cancelled, so 2 over R. 2 over R. Surface area to volume ratio of a cube with side length 1 nanometer. R changes to cube R to 10 nanometer. So for a cube, surface to volume ratio is, I can just do it without drawing this out. Equal to 6 times of surface area of each face. So there are 6 faces, each face is a squared, volume is a cube, so you get 6 over a. So it's inversely proportional to the size and diameter and the edge length. So if you are going from R1 to R2, so S by V 1 is 6 over 1, S by V 2 is 6 over 10. You take the ratios, S by V 1 divided by S by V 2 is 6 by 1 divided by 6 over 10. And we get the numerator. It should be 10. So this is a R1, this is a R2, R1 and R2, R1 10 times 2, R2 is 3 times 9. Oh, S5 V1 को ये just written as R1 को. For us, if a spherical particle radius 10 micrometer disintegrates into a group of particles with radius 10 nanometer, where the total volume remains constant, increase in the surface area is by what factor? So you have a particle 10 nanometer, so surface area becomes 4 pi r square, which is 4 pi. Now this is 10 to the power minus 6, so 10 to the power minus 5 squared. This is your initial surface area as well. Final surface area, now it's disintegrating into many smaller particles with 10 nanometer size. So the total volume will be conserved. So volume V1 is 4 by 3 pi r 1 cubed is 4 by 3 pi 10 to the power minus 5 cubed. Okay. So total volume is conserved. So n number of particles of volume V2 are formed from the initial volume V1. So n is volume of the smaller particle V2 is 4 by 3 pi r cubed. There is 10 to the power 10 into 10 to the power minus 9 cubed is equals to 4 by 3 pi 10 to the power minus 5 cubed. Cancel this. N is equals to 10. Oh, sorry. N into 10 to the power minus 8 into 3 is equals to 10 to the power minus 15. So n is equals to 10 to the power minus 15 plus 24, 10 to the power 9. So it means 10 to the power 9 smaller particles. So the surface area of all the smaller particles from S2 is equals to surface area of each atom. Each particle is 4 pi 10 to the power minus 8 squared into 10 to the power 9 is the number of particles. This value becomes 4 pi is minus 10 to the power minus 16 plus 9 is 4 pi 10 to the power minus 7. This was 10 to the power 4 pi 10 to the power minus 10. Just taking the ratios S2, S1 or S2 10 to the power minus, sorry, this S2 over S1 is 10 to the power minus 7, or 4 pi cancel over, 10 to the power minus 10, 10 to the power 3. So, 1,000 times in there's another way to calculate it. Here we conserve the volume. You could have also done this. But you just take the surface to volume ratio for a sphere. So it's 3 by r. So surface to volume ratio would remain conserved, right? So initially it was this value. It doesn't get conserved. The volume V1 and V2 are 10 volts. So initially you have surface to volume ratio of 3 over 10 into 10 to the power minus 6 or 10 micron particle. And finally, you have surface to volume ratio of 3 into 10, 3 divided by 10 into 10 to the power minus 9. Okay. We know that the total volume is conserved. So if we just take the ratio of these two, like divide these two, it will come up with surface area ratio of 10 to the power 3. Different sorry. What are the total number of nanosized particles Related if a spherical particle with 10 nanometer is about 10 micron disintegrates into 10 later. Now we just read this derivation here. Now we copy it here. Surface area 1 of the larger particle, volume of the larger particle, the total volume remains conserved. So number of small particles into volume of each small particle is equal to the total volume of the larger particles. We will tend to call names and billion nanoparticles. Number of open bonds per atom in FCC 100P. For this, FCC atom sitting on the edge and atom sitting on the base and front face. Okay, so there are 100 planes. So this is your X, Y, and Z. So this is a 100 plane. This is in the front. So if you draw it, this is how it will look. So if you do this, if you remove this 111 plane, what will happen? Will also if you see the plane behind this 111 plane, you'll see these ones. This plane formed by the face center atoms of the plane behind it. So if you see in this figure, you'll see there's atom sitting behind here, there's atom sitting behind here, there's atom sitting behind here, there's atom sitting. Okay. So similarly to this face, there is a face missing outside. Like if you imagine this, there would be a atom extended this way outside the plane. Like the next layer of atoms was supposed to be sitting over here. Oh, sorry, not here. This. It's centered, face centered over here. And the face of the top one, and this one, and this one. Just mirror image, take the reflection of these two four atoms, the face centered ones, one, two, three on the bottom and the left one. Uh, about this plane, we cut. Okay, so these four atoms are missing. Okay, have cut the crystal along this 100 plane. Okay. These four atoms are missing, but if you just see the cube, the unit cell, this is half atom missing, half atom missing here, half atom is missing here, half is missing here. So total half into four, two atoms are missing, so two bonds are missing. Okay. Yes, figure I have shown last time. So this is the plane I was talking about, consisting of these four atoms. So if you take this plane, these four atoms will be missing, and these are the one I've drawn, the dash line. So four atoms are missing, but each one is counted half in this in itself. So only two, so two atoms, two bonds are missing. And 45 minutes. I'll go over the first assignment. Assignment one. So the first question was, I think the solutions are self-explanatory, but I can go over them one by one. An example of a material with two dimensions, two of the three dimension in nanometer scale. The third one is large. So if you remember from the last session, so since one dimension is larger than nanometer scale, it's 1D material. So example of a 1D material is a nanowire or a nanorod, where your x and y two dimensions are less than are in nanometer range, and the third one length is greater than nanometer. So, mm, consider the following statement for nanomaterials. They have a very large fraction of surface atoms. This is true. We, in the first session, we calculated the fraction of atoms sitting on the surface. As we go down to nanometer scale, that fraction increases. So 1 over r as r decreases, the fraction atom surface volume this value increases, this r decreases. They have large fraction of surface atoms. If A is true, B cannot be true. They have relatively low imperfections compared to bulk material. This again is false actually, since a lot of atoms are sitting on the surface, a lot of them have incomplete bonding, which leads to surface defects. They have large surface area to volume ratio. uh, To surface area to volume ratio is just is inversely proportional to radius or diameter. So A and C are three. Okay, so this one. So quantum confinement effects, which is like your band structure becoming more discretized. These happen in a very small particles where the range is 1 to 2 nanometer. Even in nanoscale less than 100 nanometer, uh, these are not as prominent, but in quantum dots where the dots are like 5 nanometer or less than that, only then do you see the splitting of bands, energies, or changing in the band. Yeah. So in the solution, they mentioned, yeah, since these confinement effects are applied to electrons, they are really very small compared to nanoparticles. When the size of the nanoparticle starts becoming comparable to the wavelength of these electrons, that's when the confinement effect starts to play. Mm. And particles are basically considered particles are minute pieces of matter having a definite boundary. Atoms of matter, the atom grain of matter. Atom is atom. Combine multiple of these atoms forming a well-defined piece and it has a boundary. And this is a particle. Next to this together. So, which of the following material cannot be observed by optical microscope? Bulk material obviously has large, you can see them. Nanomaterials, nanomaterials. So optical microscopes are like can see have resolution power of around 250 nanometer maybe. You have a really good microscope, but yeah, usually around 1000 nanometers, 1 micrometer size particles. No, red blood cell itself, at RBC, is around 6 to 8 micrometers. RBC is quite large cell, but you can see red blood cells. Yeah. Usually cell size gain is micron size, so you can see cells inside optical microscopes. Yeah, going below that, maybe to few hundred nanometers, you can get with a good optical microscope, but below that, you cannot resolve things. Bulk nanomaterials come under, yeah, the bulk nanomaterials, as we discussed, where all three dimensions are out of your nanometer length. A, B, and C are all greater than 100 nanometers. Yes. So this is your bulk or 3D nanomaterial. However, they may be composed of uh, 0D, 1D, or 2D nanomaterials. But once a milk, it's formed the 3D. Yeah. The resolution of electron microscope is around, out of these electron microscopes can see really small particles, nanometer, millimeter. Yeah. These all can be seen by optical microscopes too. Of 1 meter, 10 meter class. You can see like with your own eyes. And actually, the newer, the high resolution HRT EMs, exactly. You can even go down to maybe picometer. This is 10 to the power 201 nanometer. Here is 300 kV. The CS corrected HRTMs, which can see individual atoms, resolve individual atoms. So atoms are picometer size. In this image, I think this is silicon. I think this is silicon. Yes, in silicon, you can see the dumbbell shape. These are individual atoms, right ones. Yeah. spacing between is 0.1. I think not in big over 13 people. Um, why is titanium oxide nanoparticles used in road paints? So why is titanium nanoparticles used to form paint for marking road signs? So titanium nanoparticles, they are white color and so they're visible from the long distance. Visible from distance. They itself are not reactive, but provide they act as a photocatalyst, oxidizing the dead particles and pollutants, maintaining their white color. So all three are correct. Since in the presence of sunlight, they photocatalyze and remove the pollutants. So they maintain their bright white color, and since then they are visible from the long distance. So BCD. They oxidize the carbonous dirt particles, keeping the surface clean for them. So nanoparticles are unique in the sense that atomic species are higher energy states. Since in nanoparticles, a lot of atoms are sitting on the surface. They are at higher energy state. Yeah, they are non-reacting. Actually, they are highly reactive. Correct. Incorrect. Possess more unsatisfied bond on the surface. Again, like they're sitting on the surface, they have unsatisfied bonds, leading to their high energy states. So, again, see, correct. Millions of decophyte. So millions decophyte are covered with millions of keratin hairs, which provide adhesive force. So they can stick to any surface. Again, this was covered in the lecture. Just go through it. What about week 2 assignment? Both of them were due last. Do any of you have any doubts in the first assignment? I can go over those questions. Maybe you can message in the chat or unmute yourself. Or I can quickly go over the previous two. Okay. Composites can be considered as blank nanomaterial because the composites are usually made up of 3D material. Let's eliminate the options. 2D mean they're saying all three dimensions are in macro scale. It's incorrect. 2D with nanometer range is two dimensions. We have more than out of nanoscale. 3D है तो it all the dimensions should be greater than it should be in macro scale. So composites are they can be 2D as well. But usually we say they have 3D because of nano material which are embedded particle in the matrix that are in the nano range. So for 3D nanomaterial, you have your bulk tube, which is embedded with small nanoparticles. Mm, So this is a bulk 3D nanomaterial. Just nanoparticles are embedded with matrix. Which are the following example of a two-dimensional nanomaterial? Two-dimensional means two dimensions are in macro scale, and only one dimension is in nano scale. So the example was nanoplates. This is less than 100 nanometers, less than less than 100 nanometers, and these two dimensions are greater than 1 meter. So quantum dots is 0D, carbon nanotube is 1D, right? Graphene is a 2D material, nanowire is again 1D. So graphene is very example of 2D nanomaterial. The thickness of a graphene sheet is in nanometer scale, the two sizes are in macro scale. Bulk nanometers are basically they can fall into category of nanoparticles, nanomaterials. There are three-dimensional nanomaterials. Again, this is an example. I have a 3D object, but it consists of it's a composite of a matrix and your uh, nanoparticles. The nanoparticle is embedded in the matrix of a metal, ceramic, and this matrix can be any material, polymer, ceramic, metal. Both both of these is correct. In which of the following, in which one of the following, the number of constituting particle is from 2 to several thousand? Bulk nanomaterial. atoms or molecules are individual entities. Nanomaterials, a single nanoparticle is a single nanoparticle made up of maybe hundreds or few atoms. Bulk nanomaterial constitute particles. Again, bulk nanomaterials will have matrix and matrix, and you have nanoparticles. So you have thousands of nanoparticles inside the single bulk material. Bulk material constitutes particles to several thousands of particles. They can also be not necessarily nano materials, even just a bulk with the grain, large grains, again thousands of grains, forming a bulk metal piece. Okay. Nanomaterials can be covered at last few sessions. Nanomaterials can be crystalline or amorphous. They have a defined crystal structure. They are crystalline or they are randomly arranged. They can be amorphous. For example, is nanoglass, which is nano-sized glassy particles. So involves a crystalline thin film deposited on a substrate having thickness in nanometer scale, where the grain size is not. What will you call such type of film are in nano dimension? This is crystalline film is deposited on a substrate. So we have a substrate. This is a substrate. This is a substrate, and we are depositing a film, so crystalline thin film on top. We're depositing a thin film on the surface. So this is thin film. Okay. So this thin film is in nanometer scale, maybe 10 nanometer. Whereas the grains, so this they have large grains, which are maybe. Will you call such type of thin film as nano dimension? Is the thickness of the nano this film is it still in millimeters? Still in nanometer. Individual grain may be larger than that, but even this grain will have thickness less than. In which one of the following nanomaterial in which one of the following nanomaterial the quantum confinement occurs in all three dimensions? So for quantum confinement to happen in all three dimensions, all three dimensions should be in nanometer scale, scale. So all three dimensions are in nanometer scale. You get 0D material, 0D. Called the self-explained. Materials three or two or one external dimension in nanometer scale is if any one of the dimension is in nanoscale, you call it a nano object. Nanoparticle will have all three dimensions in nanometer scale. Nanorod has two. Dimension in nanometer scale. Nanotube again has two dimensions. This has three dimensional dimensions in nanometer scale. It's called 0D, this is 1D, this is 1D, anything can 1D, 2D, 3D. Like that. Ah, 0D, 1D, 2D. Let's not talking about 3D. A nano object with all three dimensions in nanometer is called again, we just saw nanoparticle. Nanowire is 1D, tube is 1D, these are all 1D, and the particle is 0D. 0D means all three dimensions are getting are in nanometer scale, and their length is in micro microscopic scale. Okay. What is the primary advantage of nanomaterial or bulk materials? Primary, since they're mentioning primary, that's why they've chosen large surface area to volume. Actually, they have lower melting point, so this is incorrect. Layer structure, they may have or may not have layer structure. Better mechanical strength, again, it's not necessary to. So some composites, 3D nanomaterials embedded with yeah, from fibers or from dot something else. 0D. Particle nanoparticles, you can have better strength, but again, this is not necessary. Primary reason is the mass surface area elimination. Yeah. Okay. Any doubts in the second assignment? No, we can end session here. Just a quick reminder, even though the deadline has already passed, Just wanted to post it here. So if you want to get certificate for the exam, you had to do registration before 5 p.m. today, but that would have cost you 1,000 rupees. But still, you can do registration till 15th, till 5 p.m. on 15th Friday. You'll have to pay some late fees, maybe 500 rupees. You can check. But yeah, if you want to register for the exam, do that. You can do that after 15. Okay. Share assignment. Next assignment is due on this Wednesday. Make sure to complete it. Yeah, that's all. Thank you for attending the session here.